Welcome to this scientific lecture on self-healing emulsions, a remarkable phenomenon where emulsions spontaneously repair their own structure after damage. Before we dive into self-healing, let's establish what an emulsion is. An emulsion is a thermodynamically unstable mixture of two immiscible liquids, typically oil and water, where one liquid is dispersed as droplets in the other. Here we see an oil and water emulsion. The orange droplets represent the dispersed oil phase, while the surrounding blue region is the continuous aqueous phase. Surfactants are amphiphilic molecules that adsorb at the oil-water interface, reducing interfacial tension and providing kinetic stability to prevent immediate coalescence. A surfactant molecule has a hydrophilic head that faces the water and a hydrophobic tail that points into the oil. This creates a protective monolayer around each droplet. Now here's the fundamental challenge. Emulsions are thermodynamically unstable systems that naturally want to separate. So let's ask ourselves, why do emulsions break down over time? The answer lies in three main destabilization mechanisms: creaming or sedimentation, flocculation, and coalescence. Creaming occurs when droplets rise due to density differences. Flocculation is reversible aggregation. Coalescence is the irreversible fusion of droplets into larger ones. Coalescence is particularly problematic because it increases the average droplet size, reduces interfacial area, and ultimately leads to phase separation. But here's where it gets fascinating. Under certain conditions, emulsions can exhibit self-healing behavior. So what exactly do we mean by self-healing in the context of emulsions? The answer is that self-healing refers to the spontaneous re-breaking of coalesced droplets, restoring the original droplet size distribution without external intervention. This remarkable behavior is governed by three interconnected physical principles: surfactant dynamics, Laplace pressure gradients, and flow history effects. Let's examine the first factor, surfactant dynamics at the interface. When two droplets coalesce, the newly formed larger droplet has less interfacial area per unit volume than the two original droplets combined. The total surface area before coalescence is 4 pi r1 squared plus 4 pi r2 squared. After coalescence, the new radius r is determined by volume conservation, where r cubed equals r1 cubed plus r2 cubed. The critical insight is that A new is always less than A total. This creates an excess of surfactant molecules. Before coalescence, surfactant molecules are distributed on two separate interfaces. Red dots represent individual surfactant molecules. After coalescence, there is an excess of surfactant. Some remains at the interface while others are now in the bulk phase, creating a supersaturated state. This surfactant excess creates gradients in interfacial tension, which is the driving force for the Marangoni effect. The second critical factor is the Laplace pressure, which governs the pressure difference across curved interfaces. The Laplace pressure is given by gamma times the sum of 1 over R1 plus 1 over R2, where gamma is the interfacial tension, and R1 and R2 are the principal radii of curvature. For a spherical droplet, this simplifies to 2 gamma over R. So how does Laplace pressure contribute to the self-healing mechanism? The answer is that when droplets coalesce, the resulting non-spherical intermediate shape has regions of different curvature, creating pressure gradients that drive internal flows. An elongated droplet formed during coalescence has high curvature at the ends and low curvature at the sides. This creates pressure differences that drive fluid flow. The pressure inside regions of high curvature exceeds that in regions of low curvature. These pressure gradients, combined with surfactant redistribution, can cause the elongated droplet to become unstable and break apart, restoring smaller droplets. The third essential factor is flow history and the role of shear in the emulsion. When an emulsion experiences flow or shear, droplets are deformed and brought into close proximity, increasing the likelihood of coalescence. Under shear flow, droplets are pushed together. The arrows represent the velocity field of the continuous phase. Continued shear elongates the coalesced droplet. At this point, the droplet is highly unstable. This raises an important question. Under what conditions does the elongated droplet break up? The answer involves the capillary number, a dimensionless parameter that compares viscous forces to interfacial tension forces. The capillary number is defined as mu gamma dot r over gamma, where mu is the viscosity, gamma dot is the shear rate, r is the droplet radius, and gamma is the interfacial tension. When the capillary number exceeds a critical value, typically around 0.5, the droplet will break up into smaller fragments. Now let's put all three factors together to understand the complete self-healing cycle. The self-healing cycle proceeds as follows. Two stable droplets approach and coalesce under flow, forming an elongated droplet. This elongated droplet then breaks up due to interfacial instabilities, regenerating smaller droplets. Step 1. Two droplets collide. The thin liquid film between them drains until it reaches a critical thickness. Step 2. The film ruptures and coalescence occurs. The new droplet is in a non-equilibrium state with excess surfactant and non-uniform curvature. Step 3. Surfactant molecules redistribute, creating gradients in interfacial tension. These gradients induce Marangoni flows along the interface. Step 4. Laplace pressure differences cause the droplet to oscillate and deform. If the deformation is sufficient, the droplet elongates. Step 5. When the capillary number exceeds the critical value, capillary instability, specifically the Rayleigh plateau instability, causes the elongated droplet to break into smaller fragments. To understand self-healing quantitatively, we must consider the relevant timescales in the system. The surfactant diffusion timescale is tau surf equals r squared over d surf, where d surf is the surfactant diffusion coefficient. The capillary relaxation timescale is tau cap equals mu r over gamma. The flow timescale is tau flow equals 1 over gamma dot, the inverse of the shear rate. This leads us to ask, what determines whether self-healing will occur? The answer is the ratio of these timescales. Self-healing is favored when the surfactant can redistribute faster than the droplet relaxes. When tau surf over tau cap is less than 1, self-healing is possible because surfactant gradients can be maintained. Let's examine experimental evidence for self-healing emulsions. This graph shows experimental data of droplet diameter versus time. After a coalescence event at 20 minutes, the droplet size initially increases, but then decreases as self-healing breakup occurs. The oscillations in droplet size indicate repeated cycles of coalescence and breakup, demonstrating the dynamic self-healing behavior. Self-healing emulsions have important practical applications across multiple industries. In the food industry, self-healing emulsions are critical for maintaining texture and stability in products like mayonnaise, salad dressings, and ice cream. When these products are shaken or poured, droplet coalescence occurs, but self-healing allows them to maintain their creamy texture by regenerating the fine droplet structure. Mayonnaise is an oil and water emulsion with fine oil droplets. Ice cream contains both oil droplets and air bubbles. Both rely on self-healing to maintain stability. In cosmetics, self-healing emulsions are used in lotions, creams, and sunscreens. Self-healing ensures uniform distribution of active ingredients like vitamins, moisturizers, and UV filters, even after the product is dispensed and applied. Perhaps most importantly, self-healing emulsions are being developed for pharmaceutical drug delivery systems. Intravenous emulsions carrying hydrophobic drugs experience shear stress during injection and blood circulation. Self-healing allows the emulsion to recover its structure, protecting the drug payload. A lipid-based drug delivery emulsion contains hydrophobic drug molecules encapsulated within lipid droplets. Self-healing maintains the integrity of these carriers. How do we design emulsions with enhanced self-healing properties? Strategy 1. Optimize surfactant concentration. We need enough surfactant to create the excess needed for self-healing, but not so much that it prevents coalescence entirely. Typically, the surfactant concentration should be between 1.2 times and 3 times the critical micelle concentration. Strategy 2. Control interfacial rheology by using mixed surfactant systems or adding polymers that create viscoelastic interfaces. Strategy 3. Tailor the continuous phase viscosity. Higher viscosity slows both coalescence and breakup, so there's an optimal range. This curve shows self-healing efficiency versus continuous phase viscosity. There's an optimal viscosity around 40 millipascal seconds where self-healing is maximized. Strategy 4. Apply controlled shear history. Processing conditions during emulsion formation affect the initial droplet size distribution and surfactant organization. Let's briefly discuss mathematical modeling of self-healing emulsions. Population balance equations are used to track the evolution of the droplet size distribution over time, accounting for both coalescence and breakup. The basic form is partial n of v, t over partial t equals b of v, t minus d of v, t, where n is the number density of droplets of volume v, b is the birth rate, and d is the death rate. The birth rate due to breakup is the integral from 0 to v of k, break of v prime times n of v prime d versus prime. The death rate due to coalescence is n of v, t times the integral from 0 to infinity of k col of v, versus prime times n of v prime d versus prime. This raises the question, what determines the coalescence and breakup rate constants? The answer is that coalescence rates depend on collision frequency, which is flow dependent, and film drainage and stability, which depend on surfactant properties. The coalescence rate constant equals omega collision times p coalescence, where omega is collision frequency and p is coalescence probability. Breakup rates depend on the capillary number and the viscosity ratio between dispersed and continuous phases. Despite significant progress, there are still challenges in understanding and utilizing self-healing emulsions. Challenge 1. Predicting long-term stability remains difficult because multiple timescales interact in complex ways. Challenge 2. Scaling from laboratory conditions to industrial production introduces additional complexities in flow patterns and temperature control. Challenge 3. Real industrial emulsions often contain multiple surfactants, co-surfactants, polymers, and other additives whose interactions are not fully understood. One promising future direction is using machine learning to optimize emulsion formulations by learning from large data sets of experimental results. Another direction is developing real-time monitoring techniques using advanced microscopy and scattering methods to observe self-healing in situ. Let me summarize the key takeaways from this lecture on self-healing emulsions. First, self-healing emulsions demonstrate how thermodynamic instability can be harnessed as a built-in repair mechanism rather than just a problem to solve. Second, the self-healing phenomenon emerges from the interplay of surfactant dynamics, Laplace pressure gradients, and flow history. Third, the ratio of characteristic timescales determines whether and how efficiently self-healing occurs. Fourth, self-healing emulsions have important applications in food science, cosmetics, and pharmaceutical drug delivery. Fifth, rational design of self-healing emulsions requires careful consideration of surfactant selection, interfacial properties, and processing conditions. Self-healing emulsions represent a beautiful example of how understanding fundamental interfacial phenomena allows us to design materials with remarkable properties. Nature has been using self-healing mechanisms in biological emulsions for millions of years. Milk, for example, maintains its structure through similar principles. Advancing this field requires an interdisciplinary approach combining colloid science, fluid mechanics, surface chemistry, and materials engineering. As we develop more sophisticated formulations and better predictive models, the future of smart, responsive, self-healing emulsions looks very bright indeed.